one of the most simple enzyme mechanisms that you can imagine. When I say mechanism, I mean like the reaction scheme mechanism, like a scheme, and not an actual electron pushing mechanism for those who've already had organic chemistry. So, we would have, once again, we've been talking, you have the enzyme, you have substrate, it binds, it makes this ES complex, which is also called Michaelis complex. And now, hopefully by the end of the next couple of lectures, it'll start to make sense why, or where the name came from the Michaelis complex. And we'll say it goes on to make EP, you made a product, and then you have enzyme plus product. Okay. No, nothing new about that. But rather than looking at the free energy diagram, let's look at concentration this time with respect to time. So this is the concentration, and this is time. Okay, and in this first color, I'm going to say that is equal to free enzyme. Okay. So what you can imagine, and it doesn't matter where you pick along the x-axis, I'm going to say the enzyme concentration starts here, and I only picked right there because I'm going to be writing a lot, and I don't write very neatly, so I need some space. Okay, so we'll say that that's the point that the enzyme concentration started, at time 0. What's going to happen to the concentration of your free enzyme as time goes on? Is it going to go up, go down, or be unchanged? The free enzyme on that scheme. What happens? We have the enzyme, and what's happening to it? What's the very first step? It has to bind to the substrate. And so therefore, it's going to disappear, or it's going to decrease. Free enzyme concentration is going to go down. At some point in time, it usually won't go all the way to 0. In a perfect world, maybe it would, but usually it's not going to go all the way to 0. And then after a while, you're going to get it back, because that's the enzyme, and you should get it back at the same level. That's what. Okay, it's going to come back up. And so once again, that's the concentration of free enzyme. All right, now let's look at the concentration of substrate. What happens to the concentration of substrate? Once again, I'm going to pick just some random spot. Now hopefully it's going to make sense why I picked things that are kind of far apart since I can draw neatly. What's going to happen to the concentration of substrate with time? Go up, go down. It's going to go down. And it doesn't necessarily come back. Right, it's going to go down. Where it goes down, and it may not go all the way to 0. In a perfect world, it would. And it doesn't matter where they intersect right now. We're not having to worry about math and calculus where you have to find a common vertex or whatever it's called. That's not the important thing here. We're looking at this qualitatively. Okay. Now, in this color right here, we'll look at the concentration of the Michaelis complex, ES. At time 0, what is the concentration of ES? 0. And then it's going to take a little bit of time, but it's going to go up, right? So you can imagine, it looks like this, it goes up. And it doesn't matter how far up you take it, it's going to level off. And the reason why it's going to level off is at some point in time, either all of the enzymes are going to be bound, or you're going to start to run out of substrate. Those are the two options that you have. But it's going to level off, right? You can't go any faster, or you won't have any more than that. And then it's also going to go down, and eventually it'll start to approach 0 as well. Or you could even have it go to 0. It doesn't really matter so much. But something like that. Now I'll pick another color for EP. The concentration of EP. And at time 0, what's the concentration of EP? 0. Okay? And is it going to come faster or slower than ES when you first start to see it? Slower. It's going to take a little bit of time. You got to first make the ES and then you make the EP. And so then we know it's going to look something like this. Once again, it may go above or below ES. That's not so much important. And it's going to take a little bit longer before it starts to disappear. And it too should start to approach 0, if not go all the way to 0. I'm just running out of room. And then last but not least, we have product in that color. Hopefully you can see where we're going with this. At time 0, what's the concentration of product? 0. Okay. Is it going to be faster or slower for its formation? To first see it, I shouldn't say the rate of formation, but for you to first see it, then ES and EP. It's going to take a little bit longer, or is it going to take shorter? It should take a little bit longer, because you've got to first see ES form, then it's going to be converted to EP, and then you get product. And so it's going to look something more like this. We're just talking about the actual concentration. And then it's going to go up. And at some point in time, it will end, because in theory, you could, at the maximum amount would be to convert everything to substrate. I mean, substrate to product. So there's a lot going on, even in this simple one enzyme turns one substrate into one product kind of scenario. And in vivo, many times you need to know what individual steps are, especially if you want to do like some drug design or to look at, you know, different disease states or anything like that. You do need to know like how to do the steps, but it's really hard to tell what's going on. There's just so much information going on right here. And so in enzymology and in kinetics, what they do, I'm going to go back and revert to a different color. What they do is they split this time up. If you notice, there's a certain time that I've kind of marked off in between here, like in between those two dashed lines, where the concentration of the enzyme-bound intermediates, ES and EP, is flat. Okay, it's essentially not going up and it's supposed to be flat. I'm not the best at drawing. But it's essentially not changing with respect to time. And so they call this little region of time steady state. And so if you ever heard them talk about steady state parameters, steady state kinetics, steady state reaction, it's in this time. It's where literally the concentration of the enzyme-bound intermediates with respect to time are essentially not changing. It makes the math a lot more simple. So for those who are in calculus, the slope of this would be 0, so that's why it makes the derivative of 0. So it makes the math really more simple. The region to the left of that is called pre-steady state. And they don't give a name for the region to the right. Okay, I guess in theory it'd be post-steady state. But so in general, you can divide the studied enzyme into either pre-steady state or steady state. There's a third category called single turnover, which we will discuss as time comes up. It tells you the least amount of information. Okay, and so the way to think about it, the part that would give you the most information is this pre-steady state. Because it gives you information about every single species, P, S, E, EP, and EP and ES. But they're all changing, and so it gives you the most information, but it's the most difficult to understand. You know, it's almost like if you're just given the human genome, you know, you've got all the information to know what makes that human a human, but there's so much information there, it makes it really, really difficult. Okay. Whereas the steady state region doesn't tell you as much information, but it does allow for you to make some characterizations about it. So in the macro environment. And it does make, whenever we talk about the math, it makes the math much, much more simple. Okay. All right, so let me somehow. So in general, the different types of kinetics and kinetic experiments that we often see, one's called pre-steady state. And it tells you the most information, but it's the most difficult. I mean, ideally, that would be the greatest one to probably do under most circumstances, but technically, it's really difficult to do. And then the other broad category is steady state kinetics, which this one, they give a special name as well, called Michaelis-Menten. Menten is M-E-N-T-E-N, kinetics. And I should know that, I've forgotten. But what's interesting about one of the two, I can't remember if it's Menten or Michaelis, is, especially back in the day, one of them is female, the female scientist, and very rarely did female scientists get recognition for their work. And so, but they did for Michaelis-Menten. Okay, so it's one of the things. So there were very few famous female scientists until more recent times, especially things that have something named after them. Okay. So that's why it's called the Michaelis complex, is the ES. So I'm actually going to give you the answer for this one. The rate law for the steady state kinetics, ideally, is V, or velocity or rate, whatever you want to consider it. And I'm going to give you the answer, and then later on we'll probably talk about how it came to be. That little k, that's little k, but it's got a subscript called cat for catalytic. Okay, K-cat. Remember, they all have to have a K. And those in biochemistry, maybe you remember this equation. This is called the Michaelis-Menten equation, but it's times the concentration of E, and that's free enzyme. No, that's not right. That's total enzyme. Okay, times the concentration of S divided by capital K with the subscript N. That's called the Michaelis constant. But it is a constant. Plus the concentration of S. Give everybody a moment. Once again, they call this the Michaelis-Menten equation. And later we'll talk about where it comes from. Well, that usually takes, like if I go step by step in biochemistry 1, people can attest. I go step by step to show you how it comes to be. It will take it takes an entire hour if I don't skip these steps. But that's the answer, okay? If you notice, the order, when we talk about rate laws, like first order, zero order, second order, it's very different in the sense that this one's not straightforward. It's first order with respect to E, but with respect to S, you get a different type of function. So this, because you have an S on the top and an S on the bottom. And they don't cancel out because of that plus sign, if you think back to algebra. And so that's why the shape of this curve looks very different than what you would expect. Then, I mean, it's not linear, right? And so that's why if we draw it, V as a function of S, well, if you have no substrate, in theory, it would be 0. Okay, and so you have one point there. So we're going to draw some of you may already know the answer to this, like what the shape would look like. But we're going to use some rationalization, talk about limits and things like that from calculus. But I probably won't use the exact right vocabulary because it's been a long time since I've had calculus. let's just talk about, and you'll see the reason why. I like to refer to it in more common terms. Let's look at the limit of that equation. If the concentration of S starts to go towards 0, okay? So what would that, the way that I would explain this, like I said, I'm sure that the calculus professor would probably cringe. I would explain it as, what does this equation look like if the S starts to look like 0? Okay. As it gets really, 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 really tiny. And so Km would be so much bigger than S. You can say like Km, imagine let's say that K was 1,000. That means if S was 0.00000001, then the bottom essentially would look like Kn, because it would be 1,000.000001, which is essentially the same thing as 1,000. And so it makes the equation look like this. K cat, the E, you can't take the S out, but now on the bottom, it, only looks like Km, because Km plus S is essentially equal to Kn, because S is so tiny, right? It's approaching 0. That doesn't look like much of anything. That if I'm studying where you're studying, that would still almost look Greek to me, right? That looked really, really difficult. But if we start to look at changing to like common algebra terms, and we say that this is equal to y is equal to, and I'm just going to rearrange this. K cat E Km plus B. So what shape would that make? It's a line. And so y is equal to m. The m would be all of that. S would be the x, and then plus b, which in theory, in a perfect world, would be 0. Right? But this is your constant. That's like the mathematical fudge factor. I'm sure that's not what they would call it, but that's what I call it. So that means it's going to look something like this. Or actually, I'll try to keep the colors about the same. Okay. And once again, the slope of that at that part of the line would be equal to the stuff that I put in parentheses. We'll talk about what that means in a little bit. Let me see if I can move some of this up. Okay, good. Now let's do the exact, on the other end of the spectrum. Like, what happens if S gets huge? So S now, they always say approaches infinity. And we look back to that Michaelis-Menten equation with K cat times E times S, blah, 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 blah. What will happen to the thing on the bottom? The Km plus S, what will it approximately equal if S is infinity, or almost infinity? It's approximately equal to infinity, or S, right? Because S, now listen, we said that 1,000 before K was 1,000. What happens if, it's like the Austin Power movies, if S was a billion, gazillion, kind of thing, then you're going to have a billion, gazillion plus 1,000 is really tiny. And so now it's essentially S on the bottom. That $1 million kind of thing. Okay, so what happens then is the equation becomes more simple because it becomes K cat times E times S. But on the bottom, there's only an S because the Km is so much smaller than S. It's insignificant now. Like I said, I'm sure that they have other words that they use in calculus. I'm sure there may be other words that you use when you're thinking about calculus too. So, this can even simplify even further. What happens here? The S's literally cancel. We have an S on the bottom, and now it doesn't have that plus sign. We have an S on the top, so the S's cancel. So all of this is equal to K cat, that's a little k, times E. So if we go back to this graph here, remember we're looking at the rate as a function of substrate. Now there's not even a substrate on there. So what that means, in everyday terms, is way over here, you're going to get a flat line. Right? Because the slope is literally 0. So there's not even an S on there. You know, I think it's calculus or algebra or whatever, they call that line that it approaches, it's called the asymptote. Okay, so that would be the asymptote. It's so not straight. It's supposed to be straight, but it's not. But it's supposed to be straight. So if we now draw what this really looks like, it's going to look something like this. It goes up, and then at some point in time, it's going to approach that asymptote. So it looks like this. Does anyone remember what's that shape called? It's hyperbolic. Okay. And so, to go back all the way to the original Michaelis-Menten equation, you can always expect a hyperbolic equation in general. I don't know if they, because I don't remember specifically telling you this in calculus, you know, saying that if you get something that says y is equal to mx divided by like a constant plus x, it's going to end up being a hyperbolic function. We see this kind of thing all the time in nature and in real world applications. And now it makes sense if you think about it. Because the way I like to think about it is you think about your enzyme being like a little factory, a little machine. So I lived in Detroit for many years, so I usually talk about the car, you know, making a car factory. And so your enzyme doesn't have any substrate to make any product. And then as you start to add substrate, your enzyme's going to start making products. At some point in time, your enzyme can take no more substrate in. All the binding sites are completely full. It's working just as fast as it can. So it doesn't matter how much more substrate you add, it's petered out. It's as fast as it gets. And they give that a special term. And that's called Vmax. So this asymptote that I put in this color right here, that is the maximum velocity. That's literally what Vmax means, maximum velocity. And mathematically, what Vmax is equal to is kcat, that catalytic rate constant, times enzyme, which should make sense. You can never get any faster because you're running out of enzyme. All the enzyme is busy. Okay, so that's where they talk about Vmax. Many times, whenever you're doing this kind of, if you're trying to measure something in vivo or you're doing an experiment, you can only find Vmax. Now, if you know the actual enzyme concentration, you can find the kcat. Kcat is literally specifically tells you the catalytic rate constant. But most of the time, you're limited to only find Vmax because it's so hard to tell what the enzyme concentration is in vivo. You know, if you just look at that cell, you can't say, oh, hexokinase is equal to 2 micromolar. Now, in vitro, many times you can find this one specifically. Usually, they're going to report Vmax's instead of kcats. Okay, so it's as fast as it can ever get. Once again, this is all under that steady state. They don't do, pre-steady state doesn't necessarily look like this because things can really change. You can have labs and you can have weird looking functions. One other thing that we're assuming here is that there is no cooperativity. Think back to binding. Because if there is cooperativity, it won't look hyperbolic. Does anyone from biochemistry know what shape it usually looks? It's sigmoidal. Because it takes a little bit, there's what they call a lag. It takes a little bit of substrate to kind of keep prime the pump, get it kick started, and then it goes up and looks hyperbolic. So it's called sigmoidal. So if you see that, then you actually can't fit it directly with the same equation. You have to use the one that's for cooperativity. But once again, we're just looking at it simplistically. And a lot of times people try to manipulate it, manipulate the situation, hoping that they can do this, because like I said, the math becomes much more simple than what it would be otherwise. Okay, so that was Vmax. So to give a little bit of clarity, hopefully, let's move this over. So now we're just looking at that part. So this is just some of the vocabulary. Just to summarize, we have Vmax is literally the maximum velocity. That's how fast it could ever go. And And it's mathematically, it is equal to what's called kcat times the enzyme concentration. Okay. Kcat is called the catalytic rate constant. And it really is the little k from the rate laws. It's just, this is a very specific one. So the kind of units that you get for Vmax are always going to be a concentration per unit time because it's a velocity. However, for kcat, typically it's going to be a per unit time, right? Because the E is going to be the concentration, and so it's going to be like a per second or something. That's supposed to be K. That's K. They also, and I don't know where the number, where this nickname comes from. They call kcat a lot of times the turnover number. Which I think is a stupid name. But I just want to say that in case you see it. It will also make sense if we talk about single turnover. Because turnover, what do you suppose a turnover means? Like what does that sound like? Like what's that turnover? No.
Wonderful apple loser.
And I prefer cherry. Yes, that's what I'm thinking too. Literally, it means that means that would be the rate constant, literally for the enzyme to make one product per unit time, like to turn over once, to turn the reaction one time. So, but yeah, they did. So you can imagine if we talk about single turnover kinetics, then they literally means that you make it to where the reaction can only occur once. So it only literally tells you the rate limiting stuff. It tells you nothing else. So, but that's why single turnover literally means it can only happen one time. That's the turnover number. Turnover number is really kcat. I like to say kcat or catalytic rate constant because it's a little easier to understand talking about turnovers, especially if you haven't eaten lunch yet. So. Okay. All right. So the other thing I wanted to point out, which I actually already moved it. Let me see if I can move it back. Oh, I can. I know it gets a little sloppy. But if we look over here, at this one right here, this, once again, if you remember, was the slope towards 0. So let me move it back again. That, and so that's this part, what is that blue or green? Whatever this color is right here. That's what we drew right here. That right there, even though it looks ugly, it's got a special name, and it's actually very important. Okay. So Vmax, sometimes they call it Vmax over Km, which is the same thing. Remember, since Vmax is equal to kcat times E over Km. This kcat over Km, this is always the hardest, the most difficult thing to explain, I think, in all of, at least steady-state kinetics. Because kcat over Km looks ugly, sounds ugly, but it's very, very important. Okay, does anyone from biochemistry remember what do we call kcat over Km? Or sometimes they refer to Vmax over Km as the same thing. It's the same nickname. It's called the specificity constant, or sometimes they call it the catalytic specificity. Okay. But usually we'll call it the specificity constant. Like I said, or catalytic specificity. It seems very nebulous. First of all, it's a second order rate constant. Kcat over Km is going to be second order. Mathematically, if you solve for it, they would tell you the limit of the second order rate constants, all that kind of stuff. That's only if you're going to get into the math or the engineering behind it. When you spend some kind of bioengineering or something like that. Okay, so what does that tell you? I like to give examples. Okay, that we'll come back to it, and I'll try to come up with a real world example that will help you hopefully put an idea behind the specificity constant and what it really means. The third player, so to speak, or the third term that's used for this in these talks is Km. Km's called Michaelis constant. It's very similar to Kd, but it's an equilibrium constant or a thermodynamic constant. Mathematically, if you solve for it, this is what it looks like. It's you know how Kd would be free enzyme times free S over ES. This one's EX, and it's the summation. Okay, remember the summation. And what that means for EX is it's literally all enzyme-bound intermediates. So if you only have one step where you need ES, then Km and Kd are the same thing. But if you have ES and EP, this would be ES plus EP. However, that doesn't, that's hard to understand. Whereas when you see it on the graph, it's a little easier to understand, especially when you start talking about it with real-world examples, okay? So the way to find Km is go on your graph, the original graph up here, and if you go to half the Vmax, then you go over and you go down, just like you do for Kd. I mean, it's completely analogous. So we go to 1/2 Vmax, we go over, we go down, and that's Km. Km's always going to have the same units as your substrate. Km literally means, like in real world terms, it's the concentration of substrate needed to get half Vmax. So a lot of times they use it interchangeably with Kd, because Kd itself may be, especially if your reaction is really fast, may be hard to find a Kd, but it would be easier to find Km. But it kind of gives you a relative idea for the affinity, but not necessarily the specificity. Affinity and specificity are can be two different things. Okay, so we have 7 minutes. I want to show you an example of using this, like a real world example of using this and trying to come up with an idea of what these numbers would mean, or these terms, I should say. So what we're going to do, people from biochemistry have seen this before. Let's suppose that we've got 2 different car companies. They love my car companies. My enzyme is a car factory, and I'm not making any political statement about the different car factories. In fact, a lot of times I would ask students to name whatever their favorite car is or whatever. So let's say they're going to have a rate for how many cars that they can make, and it's cars per day, right? And so in this, instead of substrate, we're talking about money or resources, how much money we have to put in. At 0, if you have no money, you're not going to make any cars, right? So then you go up, but at some point in time, no matter how much more money you put into that, all of your assembly lines in your car factory are busy. They are full. You cannot make any more cars. That is the maximum amount of cars that factory can make. That's the total amount of product that enzyme can make. That would be your Vmax. That's where we get the Vmax. So here, this would be cars per day once again. All right, and then we're going to have our Km. Right. And you could show, it's kind of hard for me to draw it on here. It makes it stopping. That Vmax over Km would be this part right here. Okay, going towards 0. Let's give you an idea, like what we really mean. So let's start putting some numbers behind this. So what I'm going to do, or actually I guess I could do the same one. I'll just make the same graph on here. I usually do 2 different graphs. Let's say that we have 2 different car companies. We have another one, and this is what its graph looks like. Vmax, So to find its Km is going to look like right here. Now let's put some numbers to this. I'm going to try to make these numbers about the, make sense. So let's say this was 100. So the white car company can make up to 100 cars per day. That was their maximum. And is that one blue? The blue car company's Vmax would be, let's say, 75. Okay. So I'm just going to make that a little bit smaller so that way I can write. So we have the white car company. You can, if it helps you to put the name with it, you can call it GM or Ford or whatever. And then you have the blue car company. So we need to put, we'll find Vmax, Km, and then this term Vmax over Km. For each of these, the units for this would be cars per day. The units for Km is dollars, and the units for Vmax is cars per day per dollar. Okay. So let's say for the Km, let's say that this Km is 25. And maybe you guys are better judge than I am. If that's 25, do you think that that's what, about 5 maybe? Doesn't matter to me. We'll say it's 4. Or no, doesn't make it hard. We'll say it's 2. Okay. So we'll say that this one's 2. So we already know the Km. So the Km for the blue was $2. The Km for the white car company was $25. The Vmax for the white car company is 100 cars per day. And the Vmax for the blue car company was $75. 75 cars per day. Now let's say that you're going to be an investor. Which of these 2 car companies do you think you get the biggest bang for your buck? That you'd be the best one to invest in? The one that makes 100 cars per day, or the one that makes 75 cars per day? The white or the blue?
100 cars.
You know, if you haven't taken very many technology, say, oh look, they can make 100 cars in a single day. That's why I'm going to put my money in. This is where the Vmax over Km comes into effect. You take 100 and you divide it by 25, you get 4. That literally means that this car company can make 4 cars per day per dollar. This one would be 75 divided by 2. 75 divided by 2 is 37.5. So they can make 37.5 cars per day per dollar. Which one is the best car company? The better car, I should say better car company. Correct. The blue one. So you get the most number of cars in the amount of time for every dollar that you put into it. So that's why they called that Vmax over Km, K over Km. They call that the catalytic specificity or the specificity constant, because it tells you how specific that enzyme is for that particular substrate per unit time. Okay, and it's not always going to be true. You could have had one that's really, really, really fast. Like if we had one that made 1,000 in 25, and then it'd be 40, so it'd be even more specific. It'd be even better. I just wanted to pick one where it wasn't necessarily the fastest enzyme. That would be the most efficient enzyme. So in this instance, the fastest is not the most efficient, but sometimes it is the faster one would be the most efficient one, and so on and so forth. Okay, and so we'll do more examples of this kind of stuff in the days to come.